Hey everyone, so we're going to continue our discussion with the rotational motion. We're going to move on to the next part. So far we've talked about basically describing how much of a rotation the object made, which was angular displacement. We've talked about talking about how quickly it's going to make that change. So like whether it completed that rotation in 1 second or 10 seconds could tell us the angular velocity. And we've also talked about how to relate the linear values to the angular stuff. So now let's move on to the next part, which is going to be all about, talking about the angular speed changing, but this time talking about how quickly it changes, which is called angular acceleration. So again, we know that objects, when they move linearly, their speeds aren't always constant, that speed changes. Sometimes it speeds up, sometimes it slows down, but the rate at which it changes is an important aspect called the acceleration. So we're going to do the same thing. This time it's going to be referring to how quickly the angular velocity changes. So the angular acceleration is represented by alpha. This is not the letter A. Again, it's an alpha, and it's measured in radians per second squared. So angular acceleration is how quickly the angular velocity changes. If I use my same trick as before, if you recall, last time I said that, since s equals theta r, dividing theta and s by t gets me omega. V equals omega r. Doing the same thing, dividing this by time again, because it's how quickly the velocity and angular velocity change, I end up getting a equals alpha r. Now, of course, this isn't the best thing to do, only because of the fact that technically these are supposed to be change in velocity, change in angular velocity, but the point still comes across the same way, that it's the same setup. Linear equals angular times radius. Now, I should point out that that's not always going to be the case. It's only true in these cases because each of these terms are linearly related to each other. Now, this is an extremely important aspect to point out, is that linear angular acceleration is not the same thing, or the linear component of the angular acceleration is not the same thing as the centripetal acceleration. So if you recall, in the previous unit, we've talked about, when an object is moving in a circle, it experiences a net centripetal acceleration towards the center of the circle. This centripetal acceleration is what causes the object to move in a circle. Angular acceleration and its linear component, it's not the same thing as this, because this is referring to how the magnitude of the velocity and the angular velocity change. The centripetal acceleration is actually referring to how the direction changes. Remember, velocity has two components, and when we accelerate, we're changing one of those two aspects. Typically, in the linear cases, when we're just moving in a straight line, or sometimes even forwards and backwards, the acceleration will actually affect both the direction and the magnitude. Because if we're accelerating to the left while we're moving to the right, eventually that velocity stops going to the right and will start going in the direction of my acceleration. We talked about how in the one case where you do move in a circle, the centripetal acceleration is actually not changing how fast you're going, but changing the direction your velocity is pointed. So when we're moving in a circle, we have two aspects. We have a linear component of acceleration, which is related to the angular acceleration, which is affecting this magnitude, the speed that we're changing, while the centripetal is changing the direction. This actually goes back to what I said last time when we were talking about the circular motion unit, when I said that if your velocity is pointed this way and your acceleration is pointed this way, then this only changes direction and not magnitude. So this would move at a constant speed, but move in a circle. But this acceleration would be the centripetal acceleration. But if we had velocity going this way and acceleration pointed this way, then we would have both a change in the direction and an increase in the speed. And it just so happens that the horizontal component of this acceleration would be the centripetal acceleration, and this component would be essentially, I don't know how you could write it, so I'm going to write A alpha to say that this is the component of the acceleration that's related to the angular acceleration. So the acceleration that we end up getting for in the case where our speed and direction are changing at the same time is going to be a composite combination of centripetal acceleration, changing the direction, and linear acceleration, changing the magnitude. So it's going to be important to differentiate them because there's going to be some times where you actually will end up using the centripetal acceleration equation in this unit. Because, for example, if we're talking about us traveling on the Earth, yes, the Earth rotates. That's not really the same thing as moving in a circle, but we are rotating with the Earth. So technically, we are moving in a circle as well. So we have both an angular aspect and this whole centripetal aspect as well. So you want to make sure that you keep these two things separated. Now, if you hadn't guessed already, there is a rhyme with all these equations. If you recall, our first equation that we had was this: omega equals theta over t. Well, if you think about it, and I kind of said that this was a average or a constant omega, if you recall, this kind of looks very similar. This looks like the average speed equation, which was v equals d over t. But we replace the v with omega and d with theta. Well, it turns out that a lot of the equations that we have for kinematics can work the same way. For example, we have the acceleration equation, which is v equals v naught plus at. Well, what I can do is I can replace the v and v naught with omega and a with alpha to get our first angular acceleration equation. We also have the annoying x equation. X equals x naught plus v naught t plus 1/2 at squared. Once again, I could replace the x's with theta, the v with omega, and a with alpha, and I get this. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And then the last equation we had was v squared equals v naught squared plus 2a. I'm just going to write it as ax, because if you recall, technically it had like x minus x naught, but x naught's always 0. So I typically always write it like this: v squared equals v naught squared plus 2ax. Same thing that we did before, and we get this other timeless angular equation. So these equations, these three are actually on the reference table, but these equations are mirrored from the linear equations that we have. And this is actually going to be true for a lot of equations moving forward, that you'll notice that the equations that we have for the angular motion can actually be mapped and taken from one of the linear equations that we have. And this is going to make us doing some of the problems very easy, because while it can get tricky balancing a lot of these equations, one thing that you can do is when you're reading the problem, basically replace all the angular terms, get rid of the angular terms and replace them with linear terms. So replace the word angular velocity, which is velocity, and think to yourself, how would I solve this linearly? Figure out what equation you would use, and then just rewrite the equation with the angular terms in place. And if you do that, you'll pretty much always get the angular equation right. Now, there are some cases, of course, where that doesn't work all the time, but it is a very useful tool for you, especially since one of the issues that people are going to have when doing this unit is having to balance a lot of the equations. So far, in every unit, we've only really learned, a handful of equations at a time. I think for the most part, the most that we've probably learned in one unit is maybe 5 or 6, and I think that might have been energy. But for a lot of these units, we're only really juggling a handful of equations at a time. Forces was only really F net equals ma most of the time. Kinematics was these 5 equations, but it was mostly the annoying x and timeless. But in this unit, you're going to end up getting an influx of at least 15 different equations that you have to remember. And half of them aren't on the reference table. So it can get a little jarring, to be hit with, all these equations that you now have to use, having to juggle both linear equations and rotational equations and their conversion factors all together simultaneously, and be able to deal with this change in terminology almost and these new symbols. So instead of doing that, this kind of makes it a lot easier to kind of get a head start in that and start kind of getting accustomed to these rotational equations, because we don't really have a whole lot of time for you to kind of get adjusted normally like with the other equations and kind of slowly introduce this stuff. So we kind of have to hit the ground running, and one of the best ways to do that is by preparing yourself by asking yourself, how would I answer this question in the linear case? Now, what would that equation look like in the angular case? This is going to be the only question that we do. So pause video, work itself, and we'll go over in a second. All right. So the first thing that we have to do is, well, actually, before I do that part, let me actually figure out what equation to use. So again, when I read this, one of the things I want to do is get rid of the angular terms. So if I get rid of these terms and I kind of reread this, it basically asks, if the velocity decreases from 1500 to 630, what is the magnitude of the acceleration? Assume this takes 110 minutes. Okay, well, I'm given velocities. I'm given 2 velocities. I'm given an acceleration, and I'm given time. Well, the equation that makes the most sense is going to be this one, v equals v naught plus at. So from there, I can then say, well, v is just the linear omega. A is alpha. So I'm going to use this equation, omega equals omega naught plus alpha t. The one thing I do want to point out, though, is that these are not proper units. The 1500 and the 630 have to be converted from RPMs to radians per second. So go back to the previous video if you need a refresh on that. I'll just write up here that you would essentially do 1500 times pi, in this case, pi over 30. So we do that for both the 1500 and the 630. Plug that in. Also, we have to make sure that we convert the 110 into seconds. So we end up getting 65.97 radians per second equals 157.08 radians per second plus alpha 6,600 seconds. And we get our acceleration to be 1.38 times 10 to the negative 2 radians per second squared. All right, so it's actually going to be a fairly small angular acceleration. And that's pretty much it. Like I said, we'll be doing more of these types of equations and stuff as the unit goes on. And this is going to be the biggest tip that I have for you, is to try to read and work on the problem linearly first, and then correlate, convert the equations into angular, and you'll pretty much always get the equation right. Like I said, with a few exceptions, it might not work, but it's going to work majority of the time. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.